This is lecture video 24. We will cover curve sketching in this lecture video. The following box summarizes the steps that should be followed to construct the graph of a function. Firstly, you will identify the domain of your function. Next, we will compute first and second derivative. And then we will try to detect critical points of the given function, and we will identify the function's behavior at each one. Next, we will find the intervals over which f is increasing or decreasing, and as you remember, this information comes from the first derivative, right? If first derivative is positive, function is increasing. If first derivative is negative, then function is decreasing. F is decreasing. Next, we will try to find inflection points if there is any, and determine over which intervals your function is concave up and down. And this information comes with the second derivative. If second derivative is negative, function is concave down. And if the second derivative is positive, your function is concave up function. And then we will analyze if there is any asymptotes of your graph or not. Finally, by looking all those information that you have covered in the step from 1 to 6, you will start drawing your graph by also indicating the intercepts of your function. Okay, let's look at the next example and try to follow all those items in order. Okay, this is our function. We want to sketch the graph of it. First of all, we start by searching for the domain. The domain is whole real numbers, right? Because there is no point for which this function is undefined. Look at the denominator. Is the denominator 0 at any point? No, since there is no such point like x squared is -1, this function is defined for all real numbers so that the domain is from -infinity to +infinity. After detecting the domain, I think it's a good idea to detect the intercepts at this point. X-intercept, meaning that where your function cross x-axis. So you will insert y equals 0 to find the x-intercept. Y equals 0 means the image is 0, at which x the image becomes 0. So x is -1. Next, let's look at x-intercepts points. This time you will find the points where your graph crosses y-axis, y-intercept. So you will insert x equals 0. If you insert x 0, you will find y equals 1. Okay. So this means that your graph passes through this point where x is 0 and y is 1. And it passes through this point where x is -1, y is 0. Okay, next. We will compute first and second derivative of the given function. This is our function. Let's compute the first derivative. This is a quotient ratio function, so we will be applying quotient rule, which goes like derivative of the numerator times the denominator minus numerator function stays the same times the derivative of the denominator function divided by the square of the function at the denominator. If you rearrange the terms for the denominator and do necessary simplifications, you will end up with this expression. Let's compute the second derivative then. This is the function now. Derivative of this numerator function is 2 times -2x, right? And then times the second function, times the derivative of the denominator function. Okay, let me write derivative of this denominator is this times the denominator minus this function stays the same times the derivative of the denominator function, right? Times 2 times 1 plus x squared times, you need to multiply with the derivative of the insider part, right? Which is 2x divided by the square of the denominator function, so the power is 4 then. So if you do necessary simplifications, you will find this expression. Now time to find all the critical points. If first derivative is 0, what is x? X is 1 or x is minus 1. Is there any point where first derivative is undefined? Let's check. From here, there is no such point. Okay, so these are the critical points for the first derivative function. Let's do the same for the second derivative. If this is 0, then you have either x equals 0 or x equals square root 3 or x equals minus square root 3. Any function where second derivative is undefined? No, there is no such point. That's why these are the crucial points for the second derivative. Why we are computing all of them? Because we need to insert all those critical points at the sign table to detect where first derivative is positive, negative, where second derivative is positive, negative, okay? Now, behavior at the critical points, increasing, decreasing intervals, and inflection points. We will handle these 3 steps together by creating the sign table, okay? So, what is a sign table? First row will include information about the first derivative. Second row will be about the second derivative, and the third row is for f. Now, on this table, we will insert all those critical points in order, okay? So let's start from minus infinity. Then I think we have minus square root 3 here. Minus square root 3. Then what we have, I think 0. Sorry, there is also minus 1 here. And then 0. And then 1. And finally, plus square root 3. Okay. So these are all the critical points. Like this, and we have plus infinity at the end. Okay, so what happens to the first derivative function at 1 and minus 1? First derivative is 0 here, 0 here. Now we will try to detect the sign of the first derivative function from minus infinity to minus 1. You know, minus 1 is one of the roots. Over this interval, look at the values of the first derivative function, okay? For example, you can pick minus 2, insert it here, and you can see that it will always get negative values. From minus 1 to 1, for example, you can insert 0 to verify that first derivative takes positive values over here. And after the point 1, for example, insert 5, you will verify that first derivative gets always negative sign. Okay, we will do the same analysis now for the second derivative. From minus infinity to minus square root 3 over here, second derivative takes negative values. You can easily verify that by picking a number over this interval. From minus square root 3 to 0, which is the next critical point, it will take positive values. By the way, at 0, square root 3 and minus square root 3, here, and here, second derivative is 0. Now we are analyzing the signs. Between 0 and plus square root 3, second derivative takes always negative values. After square root 3, it becomes positive, okay? And then look at the first derivative information given in the first row. If first derivative is negative, your function is decreasing. If it is positive, increasing. Negative means decreasing function, right? Next, look at the second derivative information, please. Second derivative is negative, meaning that your function is concave down, down, up, up. Sorry. I look at the wrong row. So negative means concave down, positive means concave up. These two, negative, negative, concave down, down, positive, up. Now, time to combine these two information. It will be concave down and decreasing. So this part of this concave down shape is increasing. That's why we will take this portion. Okay, combine these two, up and decreasing like this, concave up, increasing, concave down, increasing, decreasing, and decreasing shape. Okay, now you will add all those shapes after one another to understand the shape of your graph, okay? It starts like this. I took this, you see, decrease, then it keeps decreasing like this, then it starts increasing, and then keeps increasing like that, and then suddenly starts decreasing, keeps decreasing in this shape. So our graph will look like this shape. This is the general shape of the graph, okay? Also, at this sign table, we can detect the behavior at the critical points. For example, at minus square root 3, you see second derivative is 0 and it changes its sign. That's why you can call this point as the inflection point now, is inflection point. Why? Because second derivative is 0 there and it changes its sign. Next, at x equals minus 1, what happens? Here, first derivative is 0 and it changes its sign, meaning that, you know, it does this kind of behavior at minus 1. I am talking about this point, so there is a local minimum point there. Is a local minimum point, okay? Then at 0, x equals 0, second derivative 0, it changes its sign. Now we are talking about this point. This is the point 0. So it is an inflection point, okay? At x equals 1, what happens here? First derivative 0, it changes its sign. So we are talking about this point now. It does this turning behavior. So there is a local max there. Local max, and finally for x equals square root 3, we are at this point now. Second derivative 0 and changes its sign. That's why this point is a very nice inflection point, okay? So we have inflection point at x equals square root 3, 0, and minus square root 3 and plus square root 3, and we have local min, local max at x equals minus 1 and x equals plus 1. Okay, so let me also indicate the point information here. This is x equals minus square root 3. This is x equals minus 1. This is x equals 0. This is x equals plus 1. And this is x equals plus square root 3, where we indicate which one of is an inflection point and which one is a local max or min. Okay, let's move on to the next step where we will analyze the asymptotes of our graph. How many different types of asymptotes we remember? We have 3 types of asymptotes, right? First, horizontal asymptote, second, vertical asymptote, and third, oblique asymptote. We will search for all of them. Okay, horizontal asymptote. To detect whether you have an horizontal asymptote or not, you look at your limit of your function as x goes to plus or minus infinity. Here is your function. If x goes to plus infinity, look at the degrees for the numerator and denominator. Their degrees are the same, 2 and 2, which means the limit will be the ratio of their coefficients. So this limit is 1. And similarly, the limit of this function as x goes to minus infinity is also 1. That's why now you can call y equals 1 line as the horizontal asymptote of your curve. Any vertical asymptotes? Okay, to detect vertical asymptotes, you search for the zeros of the denominator, right? Okay, what was the denominator here? 1 plus x squared. Is there any point which makes this expression 0? So no point like that, because x squared can never be -1. That's why there is no vertical asymptote for this function, and any oblique asymptote. So you look at the degrees. If the degree of the numerator is 1 more than the degree of the denominator, oblique asymptote occurs. But this is not the case for our function. Degrees are equal. That's why there is no oblique asymptote. No vertical asymptote and no oblique asymptote. We only have horizontal asymptote, which is y equals 1 line. Okay, we handle this part. Next, last step is the drawing the graph step. Okay, to draw the graph, you will use all the information that we created here, okay? The general shape will look like this, but also you will be careful about the asymptotes, okay? That's why now you will be, okay, let me draw the graph here together with you. You have one horizontal asymptote, which is y equals 1 line, okay? So around minus infinity, your graph is close to this horizontal asymptote, right? So you start drawing your graph from here, and you see till the point x equals minus square root 3. Okay, this is minus square root 3. You will decrease your function like this. Okay, let's draw it. And you also know the intercept information of your graph. Your graph will pass through this point, x equals -1. Okay, so your graph will pass through here where x equals -1. So let's start drawing. Start at minus infinity, you are really close to y equals 1 line, which is horizontal asymptote. It will decrease like this and intersect x-axis at the point -1. So I use this shape. Then, sorry, this is not x equals -1 point yet. Okay. Before that, we have x equals minus square root 3, and then I need to change the concavity. Okay, let's be more careful on that. So let me put this point somewhere here. And let's say this is minus square root 3. And now I am ready to draw the graph. So it does this decreasing behavior, and then it changes its concavity between minus square root 3 and -1, but still keeps decreasing and intersects y-axis at x equals -1. Then what happens? Then, okay, remember this point was another intercept, but this was the y-intercept, and from this point, I will draw a graph which is increasing with this shape till x equals 0, okay? So increasing like that, and intersects y-axis at here, where y equals 1. And then I am here now, then I will keep increasing the graph till x equals 1. Okay, let's say that this is x equals 1 point, and I will keep increasing my graph. Okay, let me draw better. Like this, maybe, okay. Point 1 is here, and like that. After the point 1, the graph will start decreasing till x equals square root 3. Okay, we can do that. X equals square root 3, it will start decreasing like this, and after square root 3, it keeps decreasing, and we know that around plus infinity, our function will be so close to this horizontal line. So I will draw a graph like this, okay? So y equals 1 is the horizontal asymptote, and I read all the information here that I analyze in the sign table to construct the graph of the function like this. And this is the graph taken from your course book. And at the graph, we can see from the graph, okay, we can see that this point is the point of inflection. Why? Because concavity is changing there. This is a concave down graph, and after this point, it becomes concave up. Also here, point of inflection point. Also here we have an inflection point because the concavity changes. But as we have here, we have a local minimum, and here we have a local maximum point, okay? All those information is already written here. And as the last thing, I want to tell you that creating this sign table is the crucial part of drawing graphs. If you create this sign table really carefully without doing any mistakes, then combining all the information together to construct the general shape of your graph will help you to draw the actual graph, okay? So please create this sign table very carefully, indicate inflection points if there is any, indicate local maximum points if there is any. Put these plus minus signs for the first derivative, for the second derivative very carefully, and then reading the first line for the first derivative, you can obtain increasing, decreasing information. This row gives you the increasing, decreasing information. Second row gives you the concave up, concave down information, you know. So reading the second line about second derivative, you will decide whether your function is concave up and down. And finally, you will combine increasing, decreasing information with the concavity information to obtain this general shape. And you will just draw this general shape very carefully, also considering the asymptotes in your Cartesian axes to obtain the actual graph, okay? So that's all for this lecture video. Thank you for your attention.